Hello, welcome to this video. We'll go over three examples that appeared in three previous exams, and we'll try to just to stress some important concepts regarding resistive networks. How do we analyze them? How do we calculate the current in different branches? How to get the power? How to get the efficiency, and so on. So we'll go over these three examples, and we'll see all these concepts. Okay, first we have this example here. We have a circuit. It has one source, 5 volts here, and our target is to find the things required. Require the total resistance. Total resistance here means the total resistance seen by the source. So from the source side, this whole circuit can be replaced by one resistance RT. The second thing that you're asking for is the power delivered by the source. So there is some current that will be drawn from that source, and the product of the voltage and the current will give us the voltage of this battery or the source here, and the current drawn will give us the total power delivered by the source, the power supplied by the source. Or it can be also written as this voltage squared divided by the equivalent resistance of the circuit. We'd like to get the total current drawn here. We'd like to find the current flowing through R3. We'd like to get the voltage drop across V6. So this is this is R6 here, and the voltage across it. And if no polarity is given, we can simply say because the current is flowing this way, it will go here that way. Then the polarity that we can assume is this one here, plus and minus. Okay, and the last thing we like to get the power dissipated in the resistances R5 and R7. So this R5 and R7. Now, when you take a look at a circuit like this one, you should immediately notice a number of things. First, let's take a look at R7. R7 is connected between this node and this node. But these two nodes are connected also through a short circuit. So this means that R7 is, we call it shorted out. It's not in the circuit, because if a current is flowing, you have a current flowing this let me just try to draw it for you. If you have a current flowing this way, the current will simply see a zero resistance path through this short circuit. So it will go through this one here, and then it will continue this way. It will simply ignore R7. So R7 is shorted out. R7 is not in the circuit. The second thing to notice, we have a current that will be drawn from the source, from the battery. This current here is called I total. This current will see three branches, then it will split into three currents. So I total is the sum of these three currents. And then this same current will flow in I4 and R4 and R5. So the current I total is the same current flowing in these three, the same current flowing in these two, is the same current flowing in the resistance R6. So these 3 points here, this one, and this one, it should be clear that they are only one node. Why? Because they are simply they are connected by a short circuit. They have the same voltage. They are represented in the circuit just 1 point. So these resistances, I can simply draw them in this way, without any problem. So this is R3, this is R2, this is R1, R2, R3, do something like this, and then I can simply draw R9, and then I have the other one is R5. So this is R4 and R5 here, and this is R1, R2, and R3. So this connection here is exactly, this one here is exactly equivalent to this one. I simply separated this node. I created a redundant piece of wire. It does not really make any difference. It is the same thing. It is a current flowing IT from here. Will split into three currents. Will combine to one current again, and then will split into two currents. So the sum of these two currents is IT. The sum of these three currents is IT. Everything exactly the same. So first, let's redraw the circuit after we get rid of R7, because R7 is shorted out. And after we'll make these 3 points at just one node, and then we'll start to analyze the circuit. So this is how the circuit now looks like. It's obvious that this resistance and this resistance and this resistance are in parallel. Why they are in parallel? Because they are connected between this node and this node. So the current flowing from the source, as we agreed, is IT, will split into three currents, this one, this one, this one, and then we will recombine again at this node, and then we will split again into two currents. And there's the same current flowing here is IT. So these three resistances are in parallel, and these two resistances are in parallel. So we can replace these three by just one resistance, and we can replace these two by just one resistance. The equivalent combination of this one, we can obtain the law for parallel combination. 1 over R equivalent is 1 over 2.2K plus 1 over 1.2K plus 1 over 3.3K. So if I get the inverse of these ones, I add them and then take the inverse of the sum, you end up by R equivalent equals 628.57 ohm. So the equivalent combination of these three, 628.57. Now, for the second one, I have 3.9K in parallel with 2.7K. So we can take the expression for two resistances in parallel. 2.7K in parallel with 3.9K is 2.7 multiplying 3.9 over 2.7 plus 3.9. So if you do that, you end up as 1.595K. Now, it should be clear. Now we know what is the total resistance of the circuit. It is this one in series with this one in series with this one, because I total is flowing in the parallel combination of these three. I total is flowing in the parallel combination of these two, and I total is flowing in this one. So the total input resistance is 820, which is this one here, plus 628 plus 1.595 kilo ohm. So I know the total input resistance. I can get the total power delivered is simply equal to this voltage squared divided by the total input resistance. So this possibility, and then I can get the total current drawn from the source, because the total current drawn from the source is equal to the 5 volts divided by the total input resistance. So this whole circuit can be replaced by just one resistance, which is the sum of this one, 820 plus 628.57 plus 1.595K. So we proceed, we replace. The circuit now has been simplified into three resistances in series. The input resistance seen from the source side, so from this side here, okay, is simply equal to the sum of the three resistances. And then when you sum this one plus this one plus this one, you end up by 3043 ohm, which is 3.043 kilo ohm. The current flowing in, which I should be consistent and call it I total, it's called I total, or I in, or I source, all of them are the same. That is it's the current drawn by the source, will be equal to the voltage divided by the total resistance. So you divide 5 volts by 3.043 kilo ohm, you end up by 1.64 milliampere. Of course, 5 by 3, and then you multiply by milliampere because you have 1K here. The power delivered by the source can be calculated through different ways. Either it is V in the E multiplied by I total, so multiply 5 by this I total here, you get 8 point something. Or you can simply say it is the battery voltage squared divided by the total input resistance. The both are exactly the same thing. So if you do this expression here or this one here, both of them will give you 8.2 milliwatts. It is 5 multiplied by 1.64 milliampere, or 5 squared divided by 3.043 kilo. Exactly the same thing. Now we are required to find the current flowing through the resistance R3. Notice that the current I total will split into three currents. One will go here in I3, it will be I3, and then I2, and then I1. So part of the current will go through R3, and part of the current will go through the parallel combination of R1 and R2. So I can simply redraw this part here something like this. This is R3, and this one here is what I'm gonna call R12. This is R12, and this one here is R3, and this is I total. Okay, so you get here I3, and then you get the remaining part of I total flowing in this one here. So this is a current divider. This is a typical current divider, but I just want to find the resistance R12. R12 is simply R1 in parallel with R2, so it's 3.3K multiplying 1.2K over 3.3K plus 1.2K. If you do that, you end up by 0.88 kilo ohm. So I3, we use the current divider expression. In order to get I3, I multiply by R12 and then divide by R12 plus R3. So you end up by this expression here. This 1.64 milliampere multiplied by 0.88 over 0.88 plus 2.2. Where did this come from? This one here is R12, and this is R12, and this one here is R3. It is a current division expression, and notice if you get the current flowing in R3, you have to use the other resistance because the current divider is the opposite. Okay? So this is great. So the one for last requirement is to get V6. V6 is a voltage drop here. This is a voltage drop across R6, and it's not that difficult to get because the current flowing here is I total. I total will split into 3 currents, and then the same I total will split into 2 currents, but these 2 currents will recombine again to give us I total because this is the same circuit. So the current flowing here is simply I total. I already calculated I total, so I can simply say that V6 is nothing but I total multiplied by V6. So again, just imagine it is a current flowing in a circuit. It's like a water flowing in a pipe, and then it splits into 3 pipes, and then recombines again, and then it splits into 2 pipes, and then recombines again, and then it flows into 1 pipe, and then it goes to the pump again. Exactly the same mechanical expression or analogy with water flow. So I can get R6. The last thing is to power dissipated in R5 and R7. There is no power dissipated in R7. Why? Because the current will flow in the short circuit and will ignore R7. So I7 is 0, and thus B7 is 0. There is no power dissipated in R7. If you want to get the power dissipated in R5, it's not a problem. What you have to do, you have I total, find the current flowing here, which is I5. I5 can be obtained by a by current division between R5 and R4, because the total current flowing in these two is I total. So I can say that I5 is equal to I total multiplying R4 over R4 plus R5. So I can get I5. Once I know I5, the power dissipated is I5 squared multiplied by R5. Okay, so these are the last 2 things required. As we said, V6, the voltage drop across R6 is this one here. This is simply I total multiplying R6 here, so 820 ohm, you end up by 1.3448 volts. Okay? We can get as well the power delivered to the resistance R5 in a different way. This one here is R4 in parallel with R5. You can find the voltage drop across this branch. So this resistance here is effectively something like this. This is R4 and this is R5, okay? R4 and R5. You can get the current as I told you, or you can simply try to find the voltage drop across this branch. And this voltage drop will be R5. This whole circuit is in series, so this is a voltage divider. The 5 volts, part of it will appear across this one here, with this drop here. And part of it will be this one, and part of it will be V6. So the voltage drop across R5 is simply the percentage of the voltage that this resistance takes. So it is 5 volts multiplying this resistance divided by this resistance plus this one. It's a voltage division. So here you have to understand that I'm making a voltage division between this resistance and the series combination of 820 ohm and 628 ohm. If you do that, you end up with V5 equal 2.62 volts. Once I have V5, I know the voltage here, I can simply say that the power delivered to R5 is V5 squared divided by R5. I have V5, I have R5, I get in milliwatts. Or you can do the way I explained earlier. You can try to use a current divider, and I recommend that you do it on your own. I use the voltage in this expression. Find the I5 through a current divider, and then calculate the power in the resistance R5 as I5 squared multiplying R5. Exactly the same thing. And as I explained earlier, there is no power dissipated in the resistance R7 because it's being shorted out. So don't be fooled if you get asked for a power in a shorted resistance, because this power will be zero. Okay, we move to discuss this example. This example looks at the first glance to be intimidating. They would like to calculate here the input resistance seen between points or terminals A and B. Between any two terminals, you see one equivalent resistance. So how do you calculate this resistance? You have to use all the rules that you have learned before about parallel combination, series combination, so on. Now, a few things to notice about this circuit. The circuit is drawn in a little bit intentionally confusing way. For example, this point here and this point here, they are the same. They are one point. So I can safely move this point to here. Why they are the same? Let's take a look. I'm gonna redraw this thing again, because it's extremely important that you understand this part here. This is R3, and this is I will eliminate this extra piece of wire. This is R1, this is R9, this is R9, and this one here is R8. Okay, so what I did here, I moved this node to here. Why is this exactly equivalent to this one? Let's apply KCL. You see that the current flowing here, which is I1, will be equal to I9 plus I8 plus I3. Okay, does the same apply here? Let's see. I1 will split into two currents, I9 and another redundant current. I'm going to call it I. But this I is equal to I8 and the I3. So if you combine these two KCL expressions, you see that the current flowing in, which is I1, is equal to I9 plus I8 plus I3, because this I is nothing but I3 plus I8. So this extra piece of wire is completely redundant. Okay, so this point has the same voltage as this one because they are shorted, and I can safely move it to here. So this will make you see the circuit in a completely different way. Now, in the same way, this point is the same way as this point. This node is the same as this node, and the same as this node. R14 is being shorted out. Why? Because it's connected between this node and this node, while there is a short circuit between the two nodes. This is a short circuit, so R14 will disappear. So now the things will start to shape. I can see that I'm going to redraw the circuit. I will make this node is the same as this node. I will make this node the same as this node, and I'm going to redraw the circuit again. And you'll see the circuit is way simpler than it looks originally, and the R14 will disappear because R14 has been shorted out. So after I made the changes I suggested in the previous slide, this is how the circuit ends up looking like. So now we can immediately see that R12 and R11 are in parallel. Why? Because they share this node here and they share this one node here. This is one node. Okay, don't be confused. This is one node. We can see as well that this branch and this branch and this branch, they are in parallel. Why? Because they share this node, and the one side this node and the other side they share this node here. So they are in parallel. Okay, we can see also one very interesting thing. Because this node is the same as this node, we could see that R8 is in parallel with R9. Why? because they share this node, which is their start, and they share also the end node, because this is just one node. Okay, so R8 in parallel with R9, R12 and R11 are in parallel, and these three resistances are in parallel. And the numbers in this example are nice. You simplify very easily, because if you have 2K in parallel with 2K, end up with 1K. If you have 6K in parallel with 3K, you get 6 by 3 divided by 6 plus 3, you get 2K. So this would be 2 kilo ohm. Here you have 2K in series with 1K, so this will give you 3K. But this 3K is in parallel with 3K, then you end up with by 1.5K. And this 1.5K is in parallel with 1K, and this will give you 0.6 kilo ohm if you do the calculations. Okay, so these three are in parallel, 3K in parallel with 1K in parallel with 3K. If you do it in the way I asked you to do, first do 3K in parallel with 3K, will give you 1.5K. 1.5K is in parallel with 1K, will give you 1.5 by 1, or 1.5 plus 1 will give you 0.6 kilo ohm. So these three are 0.6 kilo ohm, and remember this is just one node here. These two are only 2 kilo ohm, and these two are only 1 kilo ohm. So now let's redraw the circuit after we have simplified all this, and after we created one node here at this point. Now this is how the circuit looks like. It looks way nicer than when we started, and we can do further simplification. Again, simplifying resistive networks, you have to do it step by step. Here you have 2K in series with 2K will give you 4K. This 4K in parallel with 4K, another 4K, correct? Because this is one node and this is one node. So this branch and this branch share the two nodes. So the net combination of these two is just one resistance, which is 2K. Here we have 900 ohm, we have 600 ohm, this will give you 1.5K. So the circuit now is simplified to this form here. Now we can do further simplification. You have 2K in series with 1K, this will give you 3K. 3K in parallel with 1.5K will give you 3 multiplying by 1.5 over 3 plus 1.5 will give you 1K. So the equivalent resistance of this circuit is simply this one loop here. You have 1K is series with 200 ohm, is series with 300 ohm, so it will give you 1500 ohm. So the total resistance seen by from between terminals A and B, or the total resistance, we call it RT, or we call it R input, or we call it R equivalent, they are all the same. They are 1.5 kilo ohm. Okay, and the numbers in this example were particularly nice. The parallel combination gave us round numbers. Okay, let's take a look at this last example. We have this circuit here. We have three sources at the input. We have all type of combinations of resistances. We're asked to calculate the equivalent voltage source. So we'd like to replace these three by one equivalent source. We find the total resistance seen by these sources. We find the power delivered by the source. And when they say by the source, they mean by all three sources, or by equivalent source. We find the total current drawn. Of course, here in this circuit, there is some current IT flowing in. Okay. We would like to find the current I3, and notice the polarity of I3. I3 is pointing this way. And I would like to find the voltage drop V8, and notice again the polarity of V8. They assume that this is positive, negative. What if this one was positive relative to this one? Then V8 they are asking for will be negative. Okay. We would like to find the power dissipated in R7 and R9. We would like if R9 is our intended load, find the efficiency. This circuit at first glance it looks intimidating, but effectively it's extremely simple circuit. Why? This whole combination here, this whole combination is connected between this terminal, or this node, and this node. But these two nodes are shorted out by this piece of wire. So if there is a current flowing in the circuit, it will go this way, and then it will have two choices, either to go through a short circuit here, or to go to these high resistance paths. Then what's going to be doing, because current will go through the least resistive path, it will go through the short circuit. And it will completely ignore this parallel combination. So all these resistances can be ignored. And this means there is no current flowing in R7. This means that the power dissipated in R7 is 0. I don't have to worry about it even. Now, the same thing is happening here for R4. Notice what's happening with R4. R4 is connected between this node and this node. But this node is the same as this node here. This node is the same as this node here. So this means that R4 has been shorted out by a short circuit. So R4 does not exist in our circuit. It's simply shorted. So remember, this node is the same as this node. R11 is hanging in the air. It's just connected to one node. It's hanging in the air, so it does not there is no current flowing through it, and it does not have any voltage drop across it. But this means that the voltage here is the same as the voltage here. Okay, because simply there is no voltage drop across this one. So now let's try to solve it. These three sources, if you apply KVL between this point, if you go around this loop here, so I'm going to create this loop here. If you go around this loop, you'll see that the voltage between this terminal and this terminal is equal to 1 volt plus 12 volts. I mean the total source voltage. Not even applying KVL, the total source voltage. You have three sources in series. Two of them try to push current this direction. One of them is trying to push current the other way. So the net source is simply 1 plus 12 minus 3. So it will give you 10 volts. So this whole circuit has one source, one equivalent source, which is 10 volts. Okay? Now, the equivalent resistance, we have, of course, the 200 ohms still there, 120 ohms still there. And we have the other one here is 130 ohm still there. And then you have the rest of the circuit. This we'll call it R equivalent one, whatever. Okay. So can we get the source voltage? Yes, the source voltage is simply 10 volts. We've now to find the total resistance. We have now to redraw the circuit after we remove that branch because it's been shorted out. After I have removed this one R4 because it has been shorted out. After I remove the R11 because it's hanging in the air, and after I move that node to here because this one and this one are short circuit. So now when you draw the circuit, the circuit looks way nicer. I combined 120 and 130 ohm to just 250 ohm, and this is right because they are in series. The same current flowing here, the same current flowing here. So I total. So the battery supplies a voltage of a current of I total, and this current will split into R3 and then into this branch. So this branch here and this branch here are in parallel. So the total input resistance simply the series combination of these two in parallel with this one, and their equivalent resistance is in series with 250 ohm. So in just one line I can simply say the equivalent resistance seen by the source 250 ohm plus this parallel combination. This parallel combination is 8 in series R8 in series R9, and it is in parallel with 1.5K. So these two will give you 1500 ohm, 1.5K. 1.5K in parallel with another 1.5K will give you a net of 750 ohms. So this whole combination can be replaced by one resistance, 750 ohm, in series with another 250 ohm. Then the net equivalent resistance or the total resistance or the input resistance is simply 1 kilo ohm. So the number here is nice. Then what is the total current drawn by the circuit? It's simply equal to 10 volts divided by 1 kilo ohm. So this will give you a current of 10 milliampere. Now this current, part of it will go here, part of it will go here. Notice that the current will go here because of the polarity of the battery. The current in this branch will have to go this way. Will have to go this way from the top node to the bottom node. So this means that I3 they are asking for in this question will be negative, because you can get I3. It's simply a current divider. So there is a current divider between these two branches, but the current I'm going to be calculating is this one. So I can simply say that I3 is simply equal to I total multiplied by 1.5K over 1.5K plus 1.5K. So the numbers here are nice. So half of I total will go here, which is 5 milliampere, and the half of I total will go here, which is 5 milliampere. Why did I say half and half? Because this is 1.5K and this 1.5K. So I total will split into two halves. So I3 they are asking for, I can just by inspection, I can tell it's going to be minus 5 milliampere. Can I get V8? Of course I can get V8 because I have here 5 milliampere flowing this way. But when these 5 milliampere flow this way, they create a voltage drop with this polarity. So, and the value of this voltage drop is 600 ohm multiplied by 1.5 milliampere. So this will give us the value of the voltage. So this means that V8 you're asking for will be negative because the actual polarity happening is this one relative to this one. Okay, let's go to the next slide and see how we organize these concepts together. So we have already calculated the total input resistance 1 kilo ohm. We have one source, it's 10 volts. We know the power delivered by the source. It is the source squared divided by the equivalent resistance. So 100 divided by 1 kilo ohm will give us 100 milliwatts or 0.1 watts. We know the total current flowing in because I know that the total sources are 10 volts. And I know the total input resistance is 1 kilo ohm, so 10 volts by 1 kilo ohm, again 10 milliampere. I can get the current flowing in the resistance R3 because we agreed I have 10 milliampere flowing in because this 1.5K, this 1.5K, then it will be half and half. So the current flowing this way will be 5 milliampere, current flowing this way is 5 milliampere. So I3 is already minus 5 milliampere. Why did I put the negative sign? Because in the question they ask you for the current flowing from the bottom node to the top node, while the current actually flows from the top to the bottom. So you must include this negative sign. The resistance B7 has been, the resistance R7 has been shorted out. Then there is no B7. If you want to get the current flow, the power dissipated in R9, this is fine. It is simply the current, and this one here is a series combination of R8 and R9, 900 and 600. But the current flowing here is simply 5 milliampere. So I can simply say the power dissipated in R9 is 5 milliampere squared multiplied by 900 ohm. So I'm keeping in mind while I'm solving this one here that this 1.5K was equal to R9 in series R8. So if you do that, you get the power dissipated being in the resistance R9. If this is my intended load, then only 22.5 milliwatts was received by this load. But the source is delivered 100 milliwatts. So this means that the rest of the power was dissipated in the other resistances as losses. So my efficiency would be this number divided by this number, and then you multiply by 100%. So this is the last step in this question. You divide B9 by B source, the power dissipated in R9, which is our intended load, over the total power supplied by the sources. And this will give you low efficiency of 22.5%. 22.5.